Hi everyone. Well, I'm back home now. I had to go away for several weeks to work, and while I was away I didn't have a lot of free time or a good internet connection, so I wasn't able to make any more videos. But here's another video. I'm going to upload it soon. And I'm going to do this one on a simple user interface. If you can see that clearly. This is a liquid crystal display and 4 push buttons. And what I've done is I've wired the display up to a perforated board here, and this is the connector for the display, and then the keypad, the buttons are down here, and then I wired up a piece of ribbon connector and a dual row header connector here, so I can plug it into I've made an Arduino shield here that plugs into an Arduino, and I can plug the display into this connector here, and it makes a very useful rudimentary, albeit rudimentary, but a very useful user interface. And this display here is a very common display. This one happens to have 2 lines and 20 characters across each line. These displays come in various varieties, commonly 2 line by 16 characters. Sometimes there's just 1 line, 16 or 20 characters, or some displays come with 4 lines and 20 characters across. The advantage of these displays is they all use the same controller in the display, and so they all work the same way. It's the Hitachi HD 44780 controller, or whatever equivalent other manufacturers might use. But that controller is very common, and it's actually quite easy to use once you've got around some of the initialization problems that it has, but it works very well, and there's lots of software out there on the internet that you could download. I'm going to go through what I did, my software for driving this display and the keypad, because I've done something unique here. I think haven't seen anybody else do this. I've multiplexed the 4 push buttons with 4 of the data lines on the display, and that way I've saved a lot of I/O on the Arduino. The display interface is an 8-bit interface. That means you write 8 bits to the display at once, a byte at a time. But you can initialize it and set it up so that it just takes 4 bytes or 4 bits at a time, called a nibble, and you write 2 of those. You take the upper nibble and then you write the lower nibble, and it saves 4 lines or 4 I/O pins on the Arduino. And then by multiplexing the 4 push buttons with those 4 data lines, I save 4 more lines, and so I can have this complete user interface here with 4 push buttons and a display with only using 6 I/O lines on the Arduino. So I'm going to break this tutorial up into 2 videos. The first video I'm going to talk about the display, how to interface it to the Arduino, and how to write software that works around the limitations of the Arduino world and allows a more efficient way of writing to it. If you've been following some of my earlier tutorials on software, I use some of those techniques. So let's get started here, and I'll bring up the datasheet for the display. Again, if you search for HD 44780 on the internet, you'll find somewhere has a datasheet that you can download and read through it. But I'm going to go through the more important parts of it, the parts that you need to know. So let's have a look at the datasheet now.
Now here's a typical datasheet for a typical display. This is very much like mine, which has the 2-row header connector on the side here. This is one form factor that these displays come in, and I'll show you another one. And this is another form factor where the connector is across the top here. But what I want to show you with this one here is the pin assignments. What those pins mean. Let's go down to that. So obviously there's power and ground. and it runs on 5 volts. This third pin here is the, I call it the contrast control. And it's just a voltage that you set to adjust the contrast of the display so it's visible. If you don't have anything hooked up to this, it may or may not work actually. It may not be visible or it might be visible. It depends on the kind of display you have. But all you do is what they've got drawn here is you just put a potentiometer across the 5 volts and ground, and the wiper goes to this pin. The next 3 pins here are the control signals for controlling the display. This one here determines, this pin here determines whether you're writing a character to the display that's going to get shown on the screen, or if you're writing a command to the display to tell the display to do something. This is a read-write signal. If it's high, you are able to read data out of the display, basically is what you've written in it, and also to read a busy flag. I personally don't find this useful, and so I permanently tie this one to ground, and I'm always writing to the display. I never read from it. The next signal here is called the enable, and you pulse this low, high, and then low again, and that just tells the display that the data that you've put on these pins here, the data pins, is valid and ready to go. The display won't read this data until you've pulsed this pin. And now this is the 8-bit data bus that you write the characters to or the commands to. And in my setup, I've grounded the first 4 pins, DB0 through 3, because I'm not going to use them. I'm going to set this up for a 4-bit data bus rather than an 8-bit data bus. And then these upper 4 bits, 7, 6, 5, and 4, or upper 4 pins, are the ones I actually write to. And so when you still have to write a byte to the display, but using just 4 I/O pins like this, you have to write the byte twice, the upper nibble and the lower nibble. And then the last 2 pins here that actually might be absent on some displays that you have are for the backlight. And my display does have a backlight, but I don't use it. It's easy enough to hook it up to. These will run off of something a bit less than 5 volts typically, so you need to put a resistor in series with the one of these leads to drop the voltage down so that you don't burn out the backlight. If you hook it up to 5 volts, the backlight won't last very long. So those are the 16 pins on that connector. And on the other kind of displays where the connector is across the top, the same thing. The pins, I think, are even probably ordered in the same, or have the same functions in the same order. Yes, they do. It looks very much the same. So the next thing I want to look at here is the data sheet for the microcontroller that's on these displays. Now it's quite extensive, and I simply typed in HD 44780 into Google, and there are many places where I could download this data sheet for that particular controller. It's for developers who are using that controller to run a display. Most of the information in here you don't need to know because it's already been done in the display that you've bought from wherever you've bought it. But what I want to look at here are the instructions. So when you pull the RS pin low, it writes a command. One of these gets written to it, and it tells the display to do something. And there's 8 different commands, and how they are differentiated is, well, first of all, here's the data bus, DB7 through 0. These 2 here, it makes it a bit confusing. I should have drawn a line through this, but anyways, these are the RS and the RW pins. But when you're writing a command to the display, you will notice here that all the commands have the upper bit set, except for this 1 bit here, which for each command it's the next one over to the left. And any bits left over on this side of the command actually have some function, and these are the parameters for the command. And so the first 2 commands here don't have any parameters. And the first one here just clears the display, and what it does is it zeroes out the RAM, it blanks the display, you don't see any characters on it. The next command here is return home, and what it does is it doesn't affect the RAM, but it just tells the cursor, the insertion point, to go back to the first character on the first line of the display. This one here is a command I don't actually use, but it has a neat, unique, or an interesting effect. And what it does is it shifts the characters on the display left or right. And you can use it for scrolling through your what you've already sent to the display. I don't actually do that, because what I do is I just tend to clear the display and rewrite it. It's easier to do it in the software. This next command here, display on and off control, has 3 parameters. D just turns the display on or off. So if D is 1, the display is on, and whatever you've written to the character memory will be displayed on the display. If you set this to 0, the display turns off. It just goes blank. Nothing else changes though. This parameter here, if it's 1, it turns the cursor on. And if this is 1 and you set this one on or high or low, this tells you whether the cursor is blinking or not. I don't use a cursor, so this one is set to 0, and then this blinking doesn't matter. So the next command here, when I send a character to the display, I want the insertion point to move automatically. I don't want to have to tell the display where to put it every time I want to write a character to the display. I may want to move the insertion point somewhere to start a line of characters, but I only need to do that once. And this, what this command does here is it tells you, or it tells the display what direction, right or left, to move the insertion point or the display. It shifts the display back and forth, much like this other command here, but it also moves the insertion point along as well. And so I use this command to I have to set up this command, sorry. I have to set up the display to tell it that I want the cursor to move, not the display. So this bit's low, and I want it moved to the right, so this bit is high. And you only have to do this one once. Same with this one, you only have to send this one once. This command here, the function set command, is important during initialization, because this is how you set up your data bus. Initially, when the display first boots up, it comes up in 8-bit mode. And I'll go through the initialization process in the software, but this bit here tells you whether, or tells the display whether it's an 8-bit mode or 4-bit mode. The next bit here tells the display whether it's a 1-line display or 2 lines. In my case, the display is 2 lines, and I want to use both of the 2 lines. If you set this to 1 line, then you can change your font. Now the font defaults to a 5 by 8 matrix of pixels, 5 pixels wide and 8 pixels high. If you set this bit high, the font changes to 8 by 10, and the other 2 pixels below will actually overwrite the next line below. And so the 8 by 10 font is not allowed if you've selected 2-line display. So in my case, I set the data length to 4-bit, and I set this high to be to tell the display that it's going to use both lines. Now the displays have an ability for you to program into it 8 of your own kind of characters. You can draw your own specific characters, and then they become accessible through the normal way. You just send a code to it, a character to it, and it brings up that one of your designed characters. And what this does is it sets up the address that you're going to write to, because you're going to have to you have to set or clear every pixel in your character. So there's 5 columns of 8 pixels. So you write a byte, it sets the pixels in that one column, and each column has a separate address, and this just tells the display what address to start writing to. This command here, and I use it a lot, it tells the display where to put the insertion point. So I write an address to this, to the display through this command, and then the next time I write a character to the display, that's the point where the character will be displayed on the screen. Now these displays actually have a lot more RAM in them than what's actually displayed, and you can think of the display as a window in the RAM. And by shifting the display with one of these commands up here, here or here, you can slide that window along the RAM and display different text that you've put in. So you can write in, I think they're 40 characters long, but only 20 characters are actually displayed. So I can move that 20 character window and shift it left or right so that it displays some of the data that I've written further off the screen. It's a way of making the display scroll. And the final thing down here is if you read from the display, this is what you get. You get the address that you set and a busy flag. And the flag is set if the display is busy doing something, and then it is cleared when the display is ready to accept more data. So that is the command set that you can use. Like I said, I use most of these commands except for this one here. And some of these commands, in fact all of the commands except for this one here, get used only once during initialization, unless I want to change something on the display, like turn the cursor on and make it blinking, for example, and then I would use this command here. And you notice on the side here they give you an execution time. So I think they've misprinted something here. I believe the clear display also takes 1.52 milliseconds. So what it means here is that when you issue this command here, the display is going to be busy for 1.52 milliseconds until it can accept another command or data. And so if you can read the display, then you poll this bit, and that bit will be set high for 1.52 milliseconds, and then it'll go low again when the display is ready. Like I said, I don't read that bit because I don't allow reading from this display. So what I do is I simply wait that time. When I issue this command, I know that it takes this long, or this command, I know that it takes 1.52 milliseconds, so I just wait 2 milliseconds for the command to finish, and then I go back and start doing something with the display. All of these other commands, they take about, I think they're about 40 microseconds, not 37. There's some other time added to this, but I put a delay in my code of 50 microseconds to guarantee that the display is not busy if I'm going to write something else. But I'll show you that in the software. So that is the command set, and we'll get into that in the software in a minute. Let's have a look at a quick little schematic here I drew up showing how I hooked up my display to the Arduino. This is obviously not the Arduino itself, it's just the microcontroller that's on it, but I'm showing you what I/O pins I used, and you can look. I'll bring up the Arduino schematic too to show how this works. So I've chosen, well, first of all, I spent a little bit of time looking at the functionality of all the different pins here, what each pin can do. Each pin has more than one function, not just an I/O pin. You know, for example, these pins here are connected to an SD card, or this is how you program the device as well. Down here, these two pins, they're connected to the serial port. So when you use the serial.println statement in Arduino world, it's actually using these lines to communicate with the controller. So I wanted to make sure that I didn't use pins that I might want to use for something else. That being said, you can still move this around and use some of the other I/O ports as well. And the reason why I'm talking about I/O ports is because I'm not using the Arduino digital write function for setting or clearing these pins. I'm writing directly to the I/O port, which saves a lot of code space and a lot of time. And also I need to be able to look at these pins because there's going to be push buttons connected up to this as well. But anyways, here's the display. There are the 16 pins that I just talked about initially. Power and ground are here, and then the VE pin, which controls the contrast. There's a potentiometer, and there was a potentiometer on my little board. I forgot to show it to you. The read-write pin is grounded, and as are the lower 4 bits of the data bus. The RS and E pin I put down here These two can go anywhere. It doesn't really matter where they are. The way I wired it up on my breakout board, or my proto board, is here. I just put them on these two pins. And then the data bus, the 7 bits here, or sorry, the 4 bits here. So DB7 has to go to the upper pin, or the upper bit of the nibble. So a nibble is 4 bytes, or 4 bits. So that's one nibble here, PD4 to PD7. The other nibble is PD0 to PD3. So if I were to hook these 4 pins up to this nibble, for example, I would have to make sure that D7 of the display goes to PD3. It stays in the same order as I've got them here. The high order pin, the high order bit of the data bus goes to the high order of the nibble. So this is how I wired it up. It's the upper port, and then these 2 pins here. Now let's have a look at the software. So this is my software. I wrote it way back in 2012, I think, or 2011. It's been a while. I did go through it a bit recently and update it, but you can go and get offline on the internet various versions of this kind of software. I think even when you download the Arduino IDE system, it comes with something called, I think it's called Liquid Crystal library that you can use here. But I chose to write my own simply because I needed to do it differently than what the Arduino world does. And that the Liquid Crystal library that comes with Arduino uses all the Arduino functions for writing to the I/O pins. And I needed to do it differently in order to multiplex the 4 push buttons with the display. So I included these libraries here. These libraries here. Standard int just defines some integer functions, which and some integer types. For example, this is defined, and I could change this to just car and then dispense with this here, and I think it would work just as well. Program space, because I wrote a function down here that where is it, down the very bottom, it will write a string, which is a series of characters stored in memory, and at the last character, that's the string, and then it has a terminating character after the string, and that's a 0, not a digital, not an ASCII 0 or the digit 0, but a 0. Well, all the bits are 0, and that's what defines a null terminated string. So there's the printable characters, and then followed by a 0. And anyways, these ones are stored in flash in the program memory. The string is stored in program memory, and this function here just reads it out of program memory, and this function here is associated with the program space library. If your code is going to use a lot of strings, you should store them in flash and use this function to get them out of flash, because it'll save your RAM. There's not a lot of RAM on these microprocessors, and because of the C programming language, which uses a lot of RAM, you could run out of RAM pretty quick, especially if you've got, say, for example, some SD card utilities, or you're writing to a display that requires a lot of characters or a lot of data stored in memory. So anyways, I can talk about that later. Let's get into the gist of this software. And then I include, I made a library, a header file, I should say, for this library, which is here. And what I do here is I define the class HD44780, and I extend it with the class print, which comes with Arduino. That allows me to use some of the functions in the print library, which includes print line or print. You use it with the serial port, but then I can do the same thing with the liquid crystal display and use some of the functions in print. It's quite useful that way. And down here, now in this section here, I've defined some macros for the different commands. Now these two commands, as I explained earlier, don't have any parameters. You can see the 1 bit that gets set in there and everything else is 0. And then this command here has the 2 parameters. So there's the bit that's set to define that it's a command for all of these. And then these are the 2 parameters. And what I've done here is I've written a macro for the 2 different versions of this one bit, and the same with this one parameter. And when you go to use that command, you take this one, or one of these 2 and one of these 2, and OR them together, and that way it'll set or clear the bits that you need to use. So if I wanted to shift the display to the right, I would pick this guy. I'll just do it right here. And I would OR it together. This is the OR command, or the OR operator. And I wanted the cursor to shift, not the display, so I would pick this and OR it with that. And that becomes the parameter that I send to the display, the data command that I send to the display. And so I've done that for all of the different commands. I've created 2 macros for each of the bits that you would set or clear. And you just simply pick one or the other of each of these and OR them together to create the command. And let's ignore this. I don't use this anymore. These macros, they are for the set the data RAM address command. So basically it moves the insertion point where the cursor is. And so line 1 starts at 8-0. Well, 8, if you wrote that out in binary, it would be 1 followed by 7 zeros. And that's the command, if you remember. If I look back at the command here. So it's this command that I'm working with. And you see that's the 1 bit that's set. And then the rest of the bits after it are the actual address. So when I want to put the cursor on the first line into some area on the cursor, or on the first line, I simply go LCD line 1 plus the number of the position that I want to put the cursor at. Or if it's line 2 or 3 or 4. These displays come in up to 4 line displays. Mine only has 2, so I'm only going to use these 2 commands here. Another macro here, this just sets the RS bit. So if you're sending a character, the RS bit is 1. If you're sending a command, the RS bit is 0. The local data area for this class is here. And what these do is they store the actual bit for the E pin. For example, if you look at my schematic, I had the E bit on pin 2 or 3, I think. And so it would look like, if I go binary like this, and it would be that bit here. That's bit 3, 4, there. And so if you equate this to the I/O port, did I get enough here? Yes, there's 8 bits there. So the number that gets stored in there looks something like this, and it's just a bit that represents which pin on that I/O port that I'm using. And I'll show you how I get that number in a little bit. This is for the RS pin, and then this is the address, or sorry, because I'm only using half of the I/O port, but when I write to that I/O port, I have to write the whole I/O port at the same time, all 8 bits at once. And so I don't want to affect the unused 4 bits that I'm not using for the display. And so what I do is I store a mask in here, which has, if it's in binary again, the mask might look like this: 1, 2, 3, 4 ones and 4 zeros. And so that means that I would preserve the upper or the lower 4 bits and clear out. If I ANDed this number with the value I read from the port, then I would AND them together, and I would preserve whatever data that I had on that port in the lower part of the port, and I would clear all of these to 0. It's just a way for me to not affect the unused part of the port. Oops. So I'll show you how that gets used in a little bit here. Part of my initialization of the class, in my instantiation of the class, is I tell the class how many rows and columns there are in the display. In my case, there are 2 rows and 20 columns. So these numbers will be filled in with that value. It's whatever you enter in when you instantiate your class, when you want to use it. These here, as you can see with the little star, these are pointers, and they contain an address of the port for the E pin and the port for the RS pin, because remember I said that those pins could be on, they don't have to be on the D port, they could be on the B or the C port as well. And so I want to store an address for that port so I can write those particular pins. And then this one here is the data port for the display. Again, it's the address that points to the register that stores the data for the I/O port on the microcontroller that the display is hooked up to. In this case, it's port D. So this is the constructor. When you instantiate your program, or when you instantiate your class or your display, you have to tell it what port your display is hooked up to, and this, what you put in here, also tells the class whether it's the upper or lower nibble of the port, and I'll show you how to do that. This tells you, this will be the Arduino's pin number for whatever your port you're using. So in my case, I'm using Arduino pin 7, which is the upper bit of the upper nibble of port D. So I would put in here 7. And here is the pin number for the RS pin, which was 2, I think, and the E pin was 3. And then in here I put the rows and columns for the liquid crystal, or for the display. 2 and 20 would go in here. So where are we here? Oh, yes. So these values are brought in to the this is the constructor that sets up the class, and I've called up these functions here: digital pin to bit mask and port input register. And these are functions that are not documented by Arduino. You can't find them in their reference section. But if you Google for these, you'll see a lot of chatter on their forum about these functions. And what this function does is it takes the pin number, this particular function, digital pin to bit mask, it takes the Arduino pin number, so that's any number between 0 and 13, and it maps it to the bit number in the port that that pin appears on. So if we look at the Arduino schematic, and this is, again, it looks just the way I drew my my microcontroller here, my AT Mega 328. So these are the pin numbers for the Arduino pins, 0 through 13. So that function, if I give it a pin number of 3, it will return a bit, a binary number with all of these bits set to 0 except for bit 3. Or if I gave it the number 10, it would return a binary number with all its bits all the bits set to 0 except for bit 2. So that it just tells you by the 1 bit which bit in the I/O port that Arduino number refers to. It sounds a bit complicated, but it's a really useful function, because I need to know which bit on the port that we're dealing with here, because I have to be able to manipulate just that bit, because I don't want to manipulate any other bits on the port, because I might screw up something else in the software. What this does here is it returns a pointer, which is an address of the port that particular pin is on. So again, E is the Arduino number for the pin that I've hooked up to. So looking back at the schematic, of that. So that was the E pin. I can't remember what pin I used for the E pin. Say it's pin 2. So the Arduino pin 2, it would map back and give me an address to the address of port 7 in the microcontroller, or port D, sorry, in the microcontroller. If I had used one of these pins here, it would give me the address of port C. And I do that for the E, RS, and also the P pin. The P pin is the pin that determines what port the display data bus is on. And so I load up these pointers with the address of the registers that you would write to write to the ports. And I will be using these later in the software to actually do my work. I use this function again with P to get the port, the pin number, or the bit number of that pin, and this just decides whether I'm using the upper nibble or the lower nibble. So if it's the upper nibble, I will create, my mask will look like this. It will be F0. If it's the lower nibble, it will be 0F. I want to make the data port pins an output. So the LCD data port, which I got from this function here, the address of which. So here I'm writing to that address. Now, that is the base address for the 3 different registers that are used to affect the I/O ports. There's the data in register, the DIN. There's the port register, which writes the data to the pins. That actually affects the outputs of the pins. And then there's the data direction register. And so the base address -1 gives me the address of the data direction register. So what I'm doing here is taking this mask here, F0, which is in here, and I'm ORing it with what's on what's in that register, the data direction register. And wherever there's a 1, which there's the 4 bits in the F are all 1, the upper 4 bits, that makes those pins output pins. So the data direction register is written with 11100000, and the upper ones set the upper bits, the upper nibble, to output, because that's what we want to do. We want to write data to the display through that port. And here I just simplified this. I used the Arduino's pin mode to make the E and the RS pins as outputs. So that's the constructor. It sounds rather complicated, but it actually is not doing very much. It's rather simple. And in order for me to figure out how these things worked, I had to actually dig into the software that Arduino comes with. And whenever you compile your software, a whole bunch of other files are compiled in the background that you don't see, and they include these things here. And so I had to dig into their software to figure out what they were doing and what these different functions actually did. Now we need to look at the pulse E function. This just simply sets the E pin high and then low again. And the way I do that is we've already figured out which port it's on. I simply OR that 1 bit that we found from this function here, digital pin to bit mask. So I simply OR that 1 bit to the I/O port and wait 1 microsecond, and then I AND a 0. So what this tilde means here is that it just does a bitwise complement. So if the number looked like this, I think I got that. If the mask was originally looking like this, when I do a tilde, it goes and takes each of these bits and inverts them, so the zeros become 1s and the 1s become 0. So it would look like that. And when I do that and I AND it with the I/O port, I simply take that 1 bit and make it a 0. And so that's what this function is doing. It's writing 1 bit to the I/O port and not affecting the other bits on the I/O port. This bit of code here tells the compiler that I want to make this function here really small. most functions that you write, well, all functions that you write normally, before they start doing what you actually want it to do, it has to put away it has to save a bunch of variables that will get overwritten when this function runs. And so what it does is it pushes them all onto the stack, however many it needs to do that. Does the function, does the instructions that you've written here, and then at the end, before it exits, it has to pop all that stuff off the stack that it originally stored there, and that takes time. And I wanted to make this function here run very quickly, and because I'm not using any variables, I can get away with using this attribute here for the function. And so what happens is this function executes very quickly. I could use Arduino's digital write to make this pin go high and low, but the digital write function calls a lot of machine code, and it takes quite a bit of time to set the bit and then clear it again. And I want to be able to pulse this pin as quickly as possible because I don't want to spend too much time writing characters out to the display. And remember, every character or every command, you have to pulse this pin. In fact, twice, because remember, we're writing out 4 bits at a time, and we have to do that twice to get a whole byte out, a whole command out to the display. And so we have to pulse this thing twice. So that's why I wrote it this way. Now I need a function to write a nibble out to the port. So I made this function called WriteNibble that has 2 parameters. N is the nibble, and what that means is it's a byte, it's 8 bits long, but the nibble that I'm going to write out is in the lower 4 bits. And this function here assumes that. And then the next parameter here is the RS pin. What do I want to set the RS pin to, high or low? So what the first thing it does here is it simply ANDs the nibble with 0F. And so a 0F looks like this. It's got 4 zeros and then 4 ones like that. The upper order bits are high. And when you AND N with this, it will clear to 0 the upper 4 bits, and the lower 4 bits, which is the nibble that we want to write, are preserved. So whatever is in these 4 bits will remain the same. They won't get changed by this ANDing function. And so I just simply do that to clear out the upper bits to make sure there's nothing there, although it's not really necessary because they get cleared anyways. And then here I look at the RS variable, and if it's 0, I take the RS pin low. So I write a 0 out to the RS port, the pin that the RS port is on. Or if it's a 1, then I write a 1 to that pin. And then here's where I let's see. Okay, here it looks at the port mask, which we set up here in the constructor, and it just decides on what part of the port I'm using, upper nibble or lower nibble. So if it's using the lower nibble, the mask will be 0F instead of F0. This will be false, so this statement will not execute. If the port that we're writing out to the display is on the upper nibble, then we have to take the data that's in the lower nibble of N and shift it up 4 bits and move it into the upper nibble, and then write it out to the port, and that's what this line here does. And it's a little complicated, but I take the data port and I AND it with the mask, this mask here that we determined up here in the constructor, because I want to preserve the bits that are not part of the display, and then I OR in the nibble, whatever it is, the upper or the lower nibble, and then I write it back out to the data port for the LCD. And then I call this pulse E function to send the E bit high and low. And that's how you write a nibble. I've got another function here called WriteByte, and it just simply calls WriteNibble twice. But in the first one, it shifts the upper 4 bits down into the lower 4 bits of the byte and then calls the function. And then here it just takes the byte you're going to write and calls WriteNibble with that byte. So when you are writing to the display 4 bits at a time, you have to write the upper nibble first and then the lower nibble. So you write data bits 7 through 4 first and then 3 through 0 after that. Now here's the initialization routine that must be done after power up, and I will let's go look at this in a minute here. I'm just going to keep going with some of the other functions that I've written. A little aside here, I followed Arduino's description on how to make a library, and you'll see a lot of these functions here have the class name preceding it, these 2 semicolons, or the 2 colons. And there's some of these functions do not have that. For example, pulse E. This is part of the class, but I don't need it to be public. The rest of the world doesn't have to know about this function, so I don't make it part of that class, or the external or the visible part of the class. Same with WriteNibble and WriteByte. I don't need to make them visible to the rest of the world. Init I sure do, because I have to run init. I have to call init at some point in the operation of my program. So I've made that visible. So I've made it, given it the class name. And same with the following functions here, or what these are called is methods. They're not called functions in C++. They're called methods. But so this is another public method that's visible outside of this file, and it's clear, and it just simply sends the clear command to the LCD, and then it waits the 2 milliseconds that I mentioned. It took 1.52 milliseconds to do the clear command, so I just gave it 2 millisecond delay, and so that means that the microprocessor is going to sit here for 2 milliseconds doing nothing else while the display is clearing itself, and then it'll exit. And the idea is that I don't want to clear it, call clear, and then start calling other functions that are writing data or commands out to the display while it's still trying to clear, because the microcontroller, the Arduino, runs way faster than the display, and I can start writing data to it before the display is ready to accept new data. So that's why I put this delay function in here, to guarantee that the display has enough time to execute this command before I do something else to the display. Clear line, this simply clears the line that you want, the first line or the second line or the third line or whatever, and you just give it the line number. The code here is just checking to see if that number is not ridiculous. If it's a number greater than the number of lines in the actually this is incorrect. This should actually say row. I'm glad I found that. I haven't used this function before and tested it, so anyways, it looks to see if my row number is out to lunch, and if it is, it just corrects it to the maximum number of rows. It'll clear the last line if you give it an incorrect value. And then set cursor is a function that I've got down here. It just puts the cursor onto the so this is XY. So it'll be the first character of the whatever line number you've chosen here. And it's been corrected here before it gets to the set cursor. And here all I do is I write out the number of, the spaces to the display on that line, the number of rows in that line. Or no, this should be columns. I was right to begin with. So this writes out a space for every character in that line. And there's a 50 microsecond delay, of course, after, remember, you write a character to the display, it takes 50 microseconds for it to actually put it up on the display. So especially here, the microcontroller and the Arduino is so much faster than the display, it can hammer out these, in fact it would be able to write all of these bytes in less than 50 microseconds. And the display would still be busy working on the first character that you wrote to it, and it would never see the other ones. And so you'd have some problem with this function. So anyways, I write out a number of spaces or blanks to that line so it clears it, and then I set the cursor back to the beginning of the line again. this function here writes a character to the display. So it calls write byte with the character that you want to write to it, or the data you want to write, and then it uses this macro to set the RS bit high or low. I think it's low in this case to make a character, or no, it's high to write a character. So this will display something on the display. And again, I wait 50 microseconds for the display to actually do it. Now I've carefully chosen the name of this function to match the name of the write function in the print class. And the print class allows you to use this display and call the print functions, or the print line function that you use for serial. And because the print and print line functions are quite powerful, they can format data for you. So you can give it an integer, and it'll figure out what the ASCII characters are to write out that integer to the port, and it formats a string which sends it out. And so by doing it this way, I can just go lcd.print, and it will automatically format the characters for me and print it out to the display, LCD display, rather than the serial port, which is the normal way that most people are using it. And then the print function, or the write function in the print class, needs to see a return of 1. Just means that it was successful. This one here is really simple. It just simply writes an 8-bit byte out to the display and sets the RS bit to the command mode. And again, it waits 50 microseconds for the command to execute. And here's set cursor. And all it does is puts the cursor on the appropriate line in the appropriate position on that line. And again, it just does a sanity check here to make sure it's not written off the end of the line. And here is a function that I wrote called putString. With the write function here, you probably don't need to actually use this command here, or this function, or this method. But I put it in for completeness. And what this does is just takes a string which is stored in RAM and writes it out. And it looks for that 0 character at the end of the string. So when this becomes 0, the write loop fails, and it ends this function. And finally, let's look at the init method. Here it is. Now when the microcontroller in the display powers up, it takes quite a bit of time to do its housekeeping to get going. And on the spec sheet it says that you need 15 milliseconds after the power supply voltage reaches 4.5 volts. The Arduino, or the ATmega, will start up and start doing stuff way sooner than that. So before Init actually does anything, I have a delay for 15 milliseconds. So this just guarantees that there's 15 milliseconds for the display to do its thing. And it does come up ready to run, but it's not in the mode that we want to use, because it comes up in the 8-bit mode, and I want to use it in 4-bit mode here. And so this is the procedure, and this is straight out of the manual, or the spec sheet for the display, or for the microcontroller that runs the display. And you have to send this command 3 times with this kind of timing. First, wait 5 milliseconds after the first time, and then at least 100 microseconds for the next 2 times. And this basically just gets the microcontroller's display, or attention. And I only write out a nibble, and we only write out the upper part of this command because we're writing the upper nibble to the port. After we've done this, now we can send this command again, except set it to 4-bit mode. And at this point here, after another delay, the controller is now in 4-bit mode, and you can start writing other commands to it to get it set up the way you want it set up. So I described ORing together different different macros to get the bits set the way you want them to. So this is what I've done here. That's an OR symbol, or an OR operator. So this is 4-bit, 2-line, and 5x8 font. And then I set it to shift right and shift the cursor with this command. And from this point on also as well, the microcontroller in the display can act on these commands fairly quickly, so I only delay 50 microseconds, which is the standard delay. But I'm only using the WriteByte function that I wrote. I'm not using one of the public functions. What do I do here? I turn the display on. Obviously you need to do that if you're going to see anything. Personally, I don't use a cursor, so I turned it off. And for completeness, I just said no blink. And you don't need this one here because it's redundant when you turn the cursor off. And finally, I just issue this clear command to make sure that the display is actually clear. And again, it takes quite a long time to execute this command, so I give a delay of 2 milliseconds. Now, let's have a look at, this is a look at the software that I wrote for running the liquid crystal display. And this will work with up to a 4-line display. If you want a copy of this, obviously you can just stop the video at each function, because I've explained each of the functions, and then you can just hand copy this stuff into your code if you want to use it. At some point down the road, I'll probably set up a website that you guys can download stuff on from if there's enough interest. Now the next thing I want to look at is sample code written for an Arduino to actually test some of these commands. So now here is an example sketch in Arduino, in the Arduino world, to test my display and the software that I wrote for the display. So here I've defined a bunch of pins. These are Arduino pin numbers. There's a number of rows and columns. And I don't use this LED pin, I didn't put it on. This is another macro that I actually don't use. These two I don't use. This is sort of a copy from some other software that I had, and I just didn't erase a lot of the stuff here. But anyways, this line here is interesting, and this is documented in the Arduino's documentation. What I'm doing here is storing this string, flash string, in program memory and not in RAM. Most of the time that you're using strings, they get stored in RAM. Actually, they get stored in both places, flash and RAM. When you set up a string in RAM, the compiler puts aside some memory for that string and writes a bit of code with the string stored in flash, so that when you power up and start up your software, start up your program, that string that is stored in flash is now copied to RAM, and then it gets used out of RAM wherever you want to use it. What I've done here is I've put the string directly in flash, and I have to write my own software in order to get it out. Doing so saves a lot of RAM. There isn't very much RAM in the 18 mega, and so you want to be careful with how much you use, and storing a lot of strings in RAM is going to use it up really fast. So this is a way of storing it in flash, where there's a lot more flash than there is RAM. And I'll show you how to get this out of flash. Here I'm instantiating the display driver. I just call it DSPL, and all the different pins plus the rows and columns. In setup, again, I'm not using this LED pin. The code's just kind of left over. But here I run the initialize routine, which I just talked about, to make sure the display is set up the way I want to use it. So I'm now in the loop part of the software. This is just going to run over and over again. I set the cursor to the upper line leftmost character, and now I'm testing the write function, and I just write out one character at a time to the screen. And since I have the cursor auto incrementing, the cursor will just move over every time I write another character, and so it will write the next character in a blank spot on the screen. I delay for 2 seconds, and then I clear the screen, and I go on and do some more testing. I set the cursor back to 0, Actually with clear it does the same thing, but I put this in anyways. I'm going to actually test set cursor in a moment in the code. Oh, actually right here I'm testing it. So set the cursor to the first line, first character, write out this. Now this string is stored in flash, or sorry, is stored in RAM. Same with this one here. So I'm just testing the print function for extracting the string out of RAM and displaying it on the LCD. I move the cursor over to the first position of the second line and I write second line. Delay another 2 seconds, clear the display. Now I just move the cursor over. This is the first line, but I moved it to the 6th position. The way I've set up set cursor is that 0 is the first position or the first line, and then 1 would be the next one over, kind of like the index of an array. And so I write a little bit of text to the first line, and then I shift the cursor over to the second line and a different position, and I write out this text as well. I wait 2 seconds, clear it, and now I use the put string function to display this string here, which is stored in RAM. And then I move the cursor to the second line, and now I call the put string p function, which I wrote, or method. I keep using the wrong terminology here. It's a method. And then I give it the address of flash string, which is this up here. So if you just use the name, that indicates the first position of the string. This is an array of characters stored in memory. An array is just one character after the next in sequential order in memory. And this name here simply points to the first character, which is the F here. I could also, down in here, write flash string, and I could put in the index of 0. And that will do the same thing. The code will operate the same way. The compiler just does the same thing with that. And then I display it, display it for 2 seconds, clear the display, and it goes back to the beginning and just keeps doing this over and over again. So let's go over to the camera, and I'll show you what it's actually doing on the LCD. All right, here is the test software running, and oops, wrong way. Leave it like that. So it's written hello world 1 character at a time by making several calls to the same function. There's the shift, and then the bottom is the flash string, storing the strings in flash. And it's just going to do this over and over again. Pretty simple test software. Now let's have a look at the Proto Shield here, how I've done it. So here's the Proto Shield. The chip on there is a real-time clock, and there's the battery to back it up right there when the power's turned off. I'll probably do a tutorial on that chip at some point and show you how to interface to it and how to use it. But the Proto Shield comes with an SD card slot, and this is a level shifter for SD cards run on 3.3 volts, and this allows a 5 volt microcontroller to interface to the SD card. And I just hand wired all the connections here. So it's pretty simple how I've done it. This connector here is for this kind of display. I have a Nokia 5110 type display, which uses a serial interface rather than a parallel interface, and it goes on to, and I wired this connector up here for that. And I have a same kind of setup for it, where there's a bunch of keys. There's 4 keys on it, and they're multiplexed with the control lines for the display. So I may do a tutorial on how to operate that display as well. So anyways, this turned into be a rather long video on the first part of a simple user interface, just interfacing the display. On the second part of this video, I'm going to show you how to interface these push buttons to the microcontroller.
multiplexed with the display to save I/O lines. So I can have a display and a keypad using only 6 lines from the Arduino. So I hope you enjoyed this video. I know it's quite long, but all you need to do is pause it now and then to take a break. And stay tuned for part 2, which is coming up soon. Thanks for watching, and if you like this, give me a big thumbs up and send me some comments. Let me know what you think. See you next time.